Okay, good afternoon, all of you.
Good afternoon to all of you.
Any questions from assignment 3 or whatever has been covered so far? And few questions were asked about assignment 3 regarding some information that is missing. Question 1, what is the grade of steel? What is grade of concrete to be adopted? I just sent an email regarding that. And also question 3, it's a T section. So, and the width of the web is not given. That also I sent an email. Please use that information for completing the assignment. Okay. So let's get started. So the next topic is design of flanged beams. Okay. Please note that as we build up the course or as we progress, we add more things. So far what we have done is we have learned how to design a rectangular section. Okay. But if you see the roof of your in your house or even in a classroom, it consists of beams on the top of which slab is going to be there. So actually this beam and slab, a part of slab is going to act integrally with the beam. So in fact, it's going to be acting, or it's going to behave like a T section, depending on the location. Suppose this is like a floor system, okay, and this is the end beam. This is end beam, and these are intermediate beams. Over the beams you have the slab. Over the beams you have the slab, and depending on the location where the beam is there, it's going to act like a T beam or an L beam. Okay, a part of this slab is going to act along with this rectangular section to take the form of a T or a L. So if you see this T section or L section, in addition, this is what we have studied so far, rectangular cross section. And in addition to that, we have this flange. So this part is called flange, and this part, let me just use a pointer. So this part is called flange. This is what is web. Okay, and similarly, this is flange, and this is web of a L section. And what should be the dimensions that we need to consider either for analysis or for the design purpose? Code is giving some guidelines for that. Okay, how much width from the slab is going to act integrally with the beam, and under what circumstances we can assume this part of the slab acting integrally with the beam. All those details are given in the code, and we will make a note of those points in today's class. Okay, so let's go and read this one. In actual practice, slabs and beams of floors and roofs of RC construction are cast monolithically. Okay, they are casted together. It's not you cast a beam over that you are going to cast a slab. If you see the if you visit any construction site, the reinforcement cage for the beam and the slab, they will be everything will be made, and then concrete will be actually they will start concreting beam and slab together. So they are going to act in a monolithic manner. Okay, they are casted because they are casted monolithically. A part of slab will act with the upper part of the beam to resist longitudinal compression. So a part of the slab is going to also act with the beam. The resulting beam section is T-shaped for intermediate beams and inverted L-shaped for other for the end ones, or end, if the beam is the end beam, then it's you can consider it as inverted L shape. Okay, the slab forms the beam flange. Whether you consider it as a T beam or a inverted L beam, slab is going to form the flange, while the part of the beam projecting below the slab forms what is called web or stem. The effective flange width for the two cases, that is for the T shaped as well as inverted L shape, is based on uniform longitudinal compressive stresses on the flange and is governed by the specifications based on experience. And code is giving you some guidelines, what should be the width of the flange and other things. Okay. In the absence of more accurate determination, the effective width of the flange. So now in these flanged sections, we have flange as well as web. The width associated with the flange we are going to denote with BF, B's subscript F. Okay. So the effective width of flange, BF, in case of T and L beams, may be taken as follows. And for T beams, the width of the flange can be taken like this. And what is this L naught? We will see what is this L naught. BW is nothing but width of the web. If you have already solved, or if you have gone through whatever we discussed for T section, this width of the what is width of web? You should be able to know that. Okay. And this is nothing but capital DF is nothing but it's the depth of the flange, overall depth of the flange. Okay, this is overall depth of the flange, and L naught is the distance between the points of contraflexion. L naught is the distance between the points of contraflexion along the length of the beam. So we will see that. I will show you in the code book as well. So this is how width of the flange is going to be decided once the floor system layout is given to you. Suppose somebody asks you to assess the capacity of an existing beam, and you go for an inspection. During the inspection, you note down some of the points. Based on that, you can arrive at what should be the width of the effective width of the flange for both T beams as well as L beams. Okay. And but this, whatever this formula is giving, either you take that, or the effective width should be the lower out of two quantities. One is given by these two equations, depending on whether it is T beam or L beam, but in no case greater than the breadth of the web, the width of the web plus half the sum of clear distances to the adjacent beams on either side. So let me show you. Just take a note of these equations. For T beams, width of the flange is given by this formula, and for L beams, width of the flange is given by this. Please take a note of it. Okay, so now that is what is given here. That is what is shown here. L naught is this one. L naught actually in the code book. I will show you where it is given in the code book. Here, whatever those two equations that you noted, that they are given in page 37 of the code book. Okay, L naught is distance between points of zero moments in the beam. Points of zero moments are nothing but points of contraflexion, where bending moment is going to change from positive to negative. Okay, L naught is the distance between the points of zero moments in the beam, and it's given in page 37 of the code book. So you don't need to mug up these formulas, or if you repeatedly do many problems, then automatically you are going to remember these equations. Okay, width of the flange for T-beams, effective width of flange for T-beams, effective width of flange for inverted L-beams. And also code is giving for isolated beams. Let me magnify. For isolated beams, suppose you have only T section. A T beam is there. T beam in the sense some like you will be seeing these isolated cases in case of a cycle stand. Maybe if you in your hostel or somewhere or any canteen, if you have some stand or even in a bus stop, you may be seeing this. A beam on either side, you may be having slab. So that's going to be like an isolated beam. For isolated beam, the effective flange width shall be obtained as below, but in no case greater than the actual width. So you find this effective width of flange using these formulas. Okay, and you see the actual width, total width of this one flange, and whichever is less, you take that one for T beam and L beam. These are for isolated cases. This is for a floor system in which you have the intermediate beams and the end beams, such kind of things. Okay, and please note that if these beams are continuous, you have already undergone structural analysis course, so you know what is a continuous beam. A beam which is supported on or which is supported on several supports. Okay, so if this beam is continuous, over several supports, code is saying for continuous beams and frames, L0 may be assumed as 0.7 times the effective span. 0.7 times the effective span. Okay. Anyway, these are the guidelines for this effective width of the flange, because for in your the examples and whatever problems like individual problems, you may be given what is width of the flange, but suppose you are asked to assess a floor system, then how do you get this effective width of flange? Then you need to make use of these equations. Okay. And let's go a few more points, whatever is given in the code. A slab which is assumed to act as compression flange of a T beam or L beam shall satisfy the following. So before you take the slab and beam together, you need to make sure that these 2 points are satisfied. Then only slab and beam are going to act integrally or monolithically. Okay, they are going to act monolithically only if they are these 2 points are satisfied. Let's read these 2 points. The slab shall be cast integrally with the web, or the web and the slab shall be effectively bonded together in any other manner. Okay, so perfect bond is assumed, and this happens if they are casted integrally. Okay, and also another point is the main reinforcement of the slab. Main reinforcement of the slab is parallel to the beam. And what is this main reinforcement in slab and other things? When we go to the slabs, then you will understand this point in a better manner. Okay, but at this stage you can just take a note of it. If the main reinforcement of slab is parallel to the beam, and the transverse reinforcement shall be provided as given in figure 3. We'll see what is that. Such reinforcement means this transverse reinforcement shall not be less than 60% of the main reinforcement at the midspan of the slab. So this is what that figure 3 is. Okay, longitudinal reinforcement is parallel to the beam, and transverse reinforcement shall be at least 60% of the main reinforcement at the mid-span. Usually main reinforcement bending moment is going to be maximum at the mid-span. That's why the corresponding amount of steel is taken. Okay, the main reinforcement, whatever quantity that you are providing in the mid-span, at least 60%, or this transverse reinforcement should be at least 60% of that. Anyway, under these conditions, we can assume the slab and beam are going to act integrally. Okay, once these two conditions are satisfied, then I can take advantage. Instead of taking it as a rectangular section beam, I can consider it as a T section or an inverted L section. And effective width of the flange can be calculated using these two equations. Okay, and let's go further. So that is whatever those equations I showed you, those equations are what they are actually depicted here in the form of a figure, and other quantities are also shown. Capital DF is the depth of the slab, and BW is width of the web. Okay, and what else here is not indicated. You can say like the depth of the web is this one. Okay, and area of steel. So let's go further. Anyway, we went through all this. Okay, and now let's read this. The neutral axis of a T beam. So now we have a flanged section. How to go about doing analysis or design? First, let's look at analysis. Okay, first let's look at analysis, or we already looked at analysis. Okay, and at the time when we are looking at analysis, we have seen neutral axis can fall within the flange, or it can fall at the junction between the flange and web, or it can fall in the web region. Okay, so neutral axis can fall in the flange, or it can fall, or it can coincide with the junction between the flange and web, or it can coincide with here in the web region. And if it is if the neutral axis lies within the flange, what is going to happen? Whatever portion of concrete that is above the neutral axis, that only we are considering to be effective. The concrete which is below the neutral axis is considered as ineffective. So if the neutral axis is within the flange, or exactly in flush with the bottom of the flange, or passing through the junction between the flange and web, then what is going to be the area which is in compression? The area which is going to be in compression is going to be either flange to overall flange area, or a part of the flange area. So the analysis or design of that kind of beam, where neutral axis lies within the flange, is similar to a rectangular section. There is nothing, there is no difference at all. It's going to be similar to a rectangular section, because concrete below the neutral axis is considered to be ineffective even in case of a rectangular section. Okay, and the issue is going to come. The issue is going to come when the neutral axis falls in the web region. Okay, so let's read this. The neutral axis of a T-beam may be either in the flange or in the web, depending on the properties of the cross section, amount of steel, tensile steel, and strength of the concrete and steels, and the strength of the materials. If the calculated depth to the neutral axis is less than or equal to the slab thickness in the sense of flange thickness, capital DF. If the neutral axis depth is less than the slab thickness or the flange thickness, the beam can be analyzed as if it were a rectangular beam of width BF, BF is given by these formulas. Okay, for isolated case, these two equations, depending on whether it's T beam or L beam, or the previous two equations, depending on T beam or L beam, effective width can be found out. And taking it as a rectangular section, now you can consider this T beam as a rectangular section, T or L as a rectangular section, having total width as equal to the effective width BF, and the rest of the things are same. Okay, so there is not much to discuss if the neutral axis is within the flange. So now the issue comes when the neutral axis is in the web. When the neutral axis is in the web, the above argument is no longer valid, and suitable methods have to be used for design of such sections. Please note that we discussed enough about this T sections analysis of this using working stress methods earlier. Okay, and also question is given in your assignment. So now we are looking at design. Okay, so let's discuss about the design issues. Okay, so when the neutral axis is in the web, the above argument is no longer valid, and suitable methods have to be used for design of such sections. Okay, the flange then provides enough compression area to keep sigma CBC low, and the check on this can be postponed until one of the last steps. Anyway, we'll discuss about this. We'll discuss about this, or once we go through an example, it will be clear for you. The design for tensile reinforcement AST is thus assumed to be for a beam much deeper than a balanced section. Anyway, we'll see, then you will understand better. Okay, so the important point that I want to bring to your attention before we look at a workout of a problem is this one. Please note that now the width, effective width of this flange is going to be, effective width of flange is going to depend on the spacing between or it's going to depend on these quantities. Effective width is going to depend on points of zero moments, distance between points of zero moment, and it's going to depend on width of the web, and it's going to depend on the thickness of the flange. Okay, so once you have information about all this, you should be able to find what is effective width. And please note that in the design of a flanged section, what is the design of a flanged section is, flanged section comprises of slab as well as a web portion. Slab is already casted. Let's assume slab thickness and everything is already fixed. So slab thickness DF is fixed. So if slab thickness DF is fixed, and what about L naught? L naught is going to be fixed based on the boundary conditions. If it is simply supported case, if it is simply supported, L naught is going to be same as the distance between the supports. If it is if the beam is having fixed conditions, then L naught is going to be 0.7 times the effective span. Okay, so L naught is going to depend on your boundary conditions, and DF is dictated by the slab thickness that is adopted. So we don't have much choice in finding what is L naught and what is DF. Whatever it is there, we have to take those. And so what is the other quantity that is left out? That is BF. Sorry, BW. BW is nothing but width of the web. So the design of a flanged section involves finding the width of the web, and then once width of the or this effective width is known, effective width of the flange is known, the quantity which needs to be found out is width of the web and the depth of the web and the amount of steel. So these are the quantities that are the what you need to determine as a part of design of a flanged section. Okay, because the slab is already, the dimensions of slab is already fixed. So now let's see further. So how to start doing this design? So this lever arm distance, because we don't know what is the effective depth of the web. So that is unknown quantity. So we don't know a priori what is the lever arm distance. So we need to start. It's going to be a trial and error procedure for this design of a T section. So we are going to start assuming the lever arm distance as some value. What is that? Please note that when we are analyzing these T sections, I already pointed out to you about this lever arm distance, approximate value of lever arm distance. So again, same thing is written here. The average value of JD, lever arm distance, may be taken as larger of 0.9 times D. D is nothing but effective depth. Effective depth is extreme fiber in distance from the extreme fiber in compression to the location of the tensile steel or centroid of this tensile steel. That is the effective depth. So lever arm distance is taken as 0.9 times D or D minus DF divided by 2, which usually gives a value within 3% of the exact one. So we are going to start with a trial lever arm. After calculation of the once the lever arm is assumed to be this, area of steel is going to be found out. After calculation of area of steel, AST, on the basis of this estimated value of lever arm, the actual position of the neutral axis can be located, and once again, if the area of steel can be calculated, and also check whether the area of steel that is calculated with the exact value of neutral axis or the neutral axis depth matches with this value. And also we are going to see the checks on the concrete compressive stress and other things. So let's go through a problem step by step, then you will understand better how to design a T section. Okay. So let's take this problem. A T-beam, please take a note of it. Please note that here you don't need to find effective width of the flange. Effective width of the flange is already given to you. A T-beam consists of 100 mm thick reinforced concrete slab cast monolithic with 300 mm wide beam. So capital DF is given as 100 mm. Width of the web is given as BW is given as 300 mm. Effective flange width may be taken as 1200 mm. BF is taken as 1200 mm. And please note that for illustration purpose in this example, BF is directly given to you, but in reality DF you need to find out by looking at the flooring, the system floors arrangement, and then looking at the boundary conditions of the beams and other things. Okay, so effective width of the flange is 1200 mm, and effective depth is 600 mm. Effective depth 600 is nothing but the distance from the extreme fiber in compression, which is the top of the flange, to the centroid of the reinforcement, that is small d is 600 mm. Find the required steel and check the section. So please make a note, what are the dimensions that are given here? Capital DF is given, and BW is given, and BF is given, effective depth is given. Almost all the dimensions are given except the area of steel. We need to find area of steel and also check the section in the sense whether the stresses are within the limits or not, whether the stresses are within the permissible limits of concrete and steel. That is what is meant by check the section. If the moment of 200,000 Newton meter is applied and permissible stress in concrete, permissible stress in steel is given, and modular ratio is also given. And again, please note that since the beginning of this course, we are designing everything or analyzing everything, both with FE250, FE415. So same thing you do it with FE415. This is a problem statement. So if you note down whatever information that is given in the problem statement, all the geometric dimensions are given and only unknown quantity is area of steel. And also you need to check whether the stresses are within the permissible limits or not. Okay, I think some question or something is there, Professor Amlan?
Yes, I will just add some, again, basic concepts. See, in last class, there was a solution of increasing the capacity of a beam without increasing the depth by helping the compression of concrete. How was it done? Some extra steel was placed in the compressive part of the concrete, and we termed that as doubly reinforced section. Now here what we're doing is we are getting the help of the supported slab and saying that, hey, let's part of the slab be considered as part of the beam so that our area of concrete under compression increases. By this also we can increase the capacity of a beam without increasing the depth. And that's the benefit of analyzing a section as a flange section if the slab is cast integrally. It is not mandatory, but it is an option given to you so that you can, in case if you fall short of the capacity by considering it as a rectangular section, if you analyze it as a flange section, you may have the capacity more than whatever is the demand. Okay.
Okay, any questions here? Okay, let me once again explain what is designed here. Effective width of flange is given, depth of flange is given, width of the web is given, overall effective depth is given, and we need to find the area of steel. And what is big issue here? You may ask. Please note that unless I know the area of steel, I cannot estimate the neutral axis depth. Okay? Unless I get the neutral axis depth, I cannot find the lever arm distance. So unless I get the lever arm distance, I cannot estimate the to estimate the area of steel also I require lever arm distance. So this is the kind of thing. So we are going to start with a trial lever arm distance. So let the lever arm distance is taken as 0.9 times the effective depth. Effective depth is given here 600 mm, which is distance from the extreme fiber in compression to the centroid of the steel. I don't know the amount of steel, but I'm assuming that the distance is to the centroid of the steel. So that is effective depth. So lever arm is taken as 0.9 times that one. This is a trial. And using this lever arm, and the suggestion here is the JD lever arm may be taken as larger of 0.9 D or D minus effective depth minus depth, the half of flange depth. So out of these two, whichever is larger. So those two quantities are calculated, 0.9 times D and also small d minus half of the flange depth. That is also calculated. Whichever is the large, that is taken as a trial, taking trial lever arm as 550 mm. So once you know the lever arm, you know what is the moment this beam has to withstand, 200,000 Newton meter. So 200,000 multiplied by 1000, because we want to convert this meters into millimeters, divided by, we need to find area of steel, divided by permissible stress in steel, multiplied by the lever arm distance. So permissible stress in steel for Fe250 is 140. So this is the approx. Please note that we don't know really the actual lever arm, because at the initial stage we don't know what is the area of steel. Until we get area of steel, we don't know the exact value of lever arm. But the problem is, unless you know the lever arm, you will not be able to estimate the area of steel. So we started with the trial lever arm, and we got an approximate value of approximate area of steel. Once we got this approximate area of steel, then we can take that approximate area of steel, and then determine the neutral axis depth. How do you determine neutral axis depth? Equating the areas of equating the moments of area in compression to the moment of area in tension. If you have already analyzed the T section, you know how to determine the neutral axis depth. Now the area of steel is known, all the quantities are known: width of the web, effective width of web, depth of the web, effective width of flange, depth of flange, effective depth, and also the web, depth of the web. Depth of the web is actually effective depth is given as 600 mm, and the thickness of flange is given as 100 mm. So this distance is going to be 500 mm. So that is going to be your effective depth of the web. So once you have this kind of shape, you can easily find what, assuming the neutral axis to be in the web region. Assuming neutral axis to be in the web region, we already discussed for this kind of shape how to estimate the total compressive force, how to take the moments of the total compressive force about the neutral axis, and finding the lever arm distance, finding the location where the resultant compressive force is going to fall. All that we have discussed. Okay. For doing that, you require to know what is the stress in concrete at the junction of flange and web at this point. At this point, what is going to be the stress? And if the extreme fiber stress is sigma CBC prime, if the extreme fiber stress is, let's say it is denoted with sigma CBC prime, then you can easily estimate what is going to be the stress here at this level. Assuming stress to have linear variation. That is what is written here. Sigma CBC prime 1, which is at the bottom of flange, is given by this distance divided by the neutral axis depth. Okay, and so sigma CBC prime 1, once you know the neutral axis depth, you can easily find what is sigma CBC prime 1 in terms of the extreme fiber stress in concrete. And neutral axis depth is self-explanatory. It is nothing but this area. You see, this entire the T portion is divided into rectangle and two rectangles. 1200 multiplied by n divided by 2. Okay, and 1200 multiplied minus, this entire thing is taken as a rectangle. One rectangle, and then these two rectangles are subtracted. So that is what is done. 200 minus 300, 1200 minus 300 is this portion plus this portion. So the total width is going to be 1200 minus 300. If you want this portion alone, it's going to be 1200 minus 300 divided by 2, and the two portions are there, so times 2. So 1200 minus 300 multiplied by the lever arm distance. Lever arm distance of this portion is going to be n minus 100. So this total depth is n, and this thickness is 100. N minus 100 divided by 2. So it's going to be here. Okay, that is what. So you please cross check this relation, and everything is known here using the approximate value of area of steel. You can easily find the neutral axis depth. And neutral axis depth, it turns out in this case it is 166.5 mm, which is actually greater than the depth of the flange, so it's going to fall in the web region. So that is what is checked. And also the stress at the bottom of the flange is expressed in terms of extreme fiber stress. So why all this is being carried out? Because I need to find where the resultant compressive force is going to act. All the details are given. You can go through that. Okay. This we already discussed. How to get the resultant, location of resultant of compressive force. And once you get the location of resultant of compressive force, you just go through this and check for any numerical errors. So the resultant compressive force is going to be located, for this example, it's going to be located at 46.42 mm from the top. So the lever arm distance is going to be overall effective depth, which is 600 minus this distance, 46.42 mm. So that is going to give you the lever arm distance. So now you know with this you initially started with trial lever arm and got the approximate area of steel. Using that approximate area of steel, again you determine the lever arm. Again you find the area of steel. If this area of steel, if the amount of area of steel that you get here is in close agreement with whatever approximate value of area of steel that you started out with, then you can stop the iteration. Otherwise you need to do one more iteration. Okay. Since there is not much difference between the exact and approximate values of area of steel, then you can proceed further. Check of the compressive stress on concrete can be carried out on the basis of approximate AST. And how do you get the extreme fiber stress in concrete? How do you get extreme fiber stress in concrete? The moment applied divided by total compressive force multiplied by the lever arm. So that is going to give you the extreme fiber stress in concrete, and then check whether that extreme fiber stress in concrete is less than the permissible stress in concrete. Okay, so this is what actually design of a T section means: finding area of steel and checking whether stresses are within the limits or not. And same calculation, just 1 second, same calculation is repeated with Fe415 steel, and here also a check is made. Okay, any questions?
Yeah, there is a question regarding that why it is n minus 100. See, essentially what is done is, whenever there is a non-rectangular section, it is considered to be summation or addition of different rectangles. How you do it is left up to you. In this particular example, what they have done is they have taken a big rectangle, the circumscribing rectangle, which is 1200 times n, and from there they have subtracted two small rectangles. This is one approach. The other approach could have been, you take the portion above the web, that as one rectangle, and the two outstanding portion of the flanges can be considered as two additional rectangles. You know, these are two ways of doing things. Just you have to be careful. I mean, whenever you do, please make sure that your calculations are correct.
Anyway, at the time of analysis of a T section, we discussed enough. It was illustrated two ways of doing this in an example. You please, I think you have missed it out, that lecture. You please go through it. Okay. Same thing is adopted here.
Yeah.
Basically, since the issue here is, if the neutral axis falls in the web, then all this you have to do. Otherwise, if neutral axis is within the flange region, then this resultant compressive force, finding the location of resultant compressive force, all this can be avoided because you can consider it as a rectangular section. Okay. So what I suggest is you think about this. So this is the design of a T section, or same here it is taken as a T section. Instead of that, you can also have only this. Suppose if this flange on this side is not there, flange on this side is not there, then it's going to become an inverted L. So the procedure is going to be same. So okay, so you please go through this example, and then let's discuss further. In next class, we'll have some discussion on this, as well as how to arrive at economical depth for a T section and other things. A small portion is left out that we'll discuss in next class. Any questions? Any questions or comments? Why class strength is so low, 71 or 70? Any questions? Professor Amlan, any other comments are there?
Yeah, I would just say that right now the way we are studying the flange section is the simpler type, means like a slab integrally connected or cast along with the beam. We can also have flange sections which are like it was mentioned that as if they're individual units. There can be a flange section which are like composite units. That means you first cast a web and then cast a slab separately, but then you should have something connecting them, and that is called shear connectors. These and the section may not look like a T even. The section can even look like a box. A box section can also be treated like a flange section. That means this type of options you may see in practice, but right now for this course, I think just a T section or an inverted L section is good enough.
And please note that I'm going very slow because these concepts are very, very important. And please note that we are in working stress method. And when we go to the limit state method, only the relationship or the stress strain diagram is going to be changing. So the stress distribution diagram is going to be different for limit state. So if you grasp all these whatever concepts that we are learning with this working stress method, and it's easy for you to follow the limit state method. Okay. Anyway, I'm going to stop here and let's meet next week, and then please attempt all the questions in assignment. By this time, you should be ready to answer all the questions. Thank you.